Let's continue. So now we have Bruno Staffa from the University of Toronto who will tell us about Weyl Law for one-cycles and applications.
Okay, thank you very much for the presentation and for the invitation. I'm very happy to be here. So the title of the talk is Weyl Law for one-cycles and applications. So I will start talking about the applications and then motivate what this Weyl Law for one-cycles is. So first we start with a compact manifold, and we will consider closed geodesics on it, which is an object that has already appeared in the previous lecture. So we can describe them as critical points for the length functional, right, on the space of closed curves in a manifold. So for every one parameter family of closed curves through our closed geodesic gamma 0, the corresponding derivative of the length at time 0 must be equal to 0 for any variation that we pick. Well, some examples are like the round sphere. We just take the equator or any great circle, or on the right, like some Dumbbell-shaped sphere. We have those three curves that represent closed geodesics. And another example, for example, when we can something that is immersed but maybe not embedded, is you can consider like this, like three-leg starfish. So it's diffeomorphic to a sphere, but with this sort of Riemannian metric. You can think of it embedded in R3. And then we can find a closed geodesic here, which sort of does this, like it goes around one of the legs and then comes back, goes around again. So this one is like immersed but not embedded, for example. Okay, so some natural questions that we can ask, for example, on surfaces, on closed surfaces, is with a Riemannian metric, whether they admit any closed geodesic, right? So for the case of non-simply connected surfaces, this can be answered simply. So for example, one can consider a loop which is non-contractible on these surfaces and find another closed curve which is homotopic to this loop and which minimizes the length among all curves which are homotopic to that one, just by taking a minimizing sequence that converts to this infimum and using Arcelus-Colli theorem, for example, or also using Birkhoff shortening flow. One can do a construction like this. But when the manifold is simply connected, so for a sphere, like the problem is that this infimum could be 0 because, well, precisely because basically every curve is contractible. Birkhoff in 1917 showed the existence of closed geodesic on any Riemannian 2 sphere, right? So it's a sphere with any Riemannian metric. And then he introduced the min-max method that will appear later in the talk, and that has also appeared in previous talks by, for example, Jinzhou and Andre Neves, and also by Rafael, the last one. So another existence result for closed geodesics on spheres by Liustenegger Schneiderman is that every Riemannian sphere admits at least 3 different embedded closed geodesics. So now that we know that in all of the cases for surfaces we have at least one, we can wonder like if there is more than one, like how many there are. And in fact, the answer is that there are always infinitely many of them. So by the works of Franks, Banger, and Hingston, every Riemannian surface admits infinitely many closed geodesics, immersed closed geodesics. Okay, but so then we can ask like how these geodesics sit on the manifold. So for example, if I pick an arbitrary open set of my surface, then does it intersect any closed geodesic? Or in other words, if I consider the union of all closed geodesics on my surface, is that a dense set of the manifold? And we also can ask for a quantified version of this. which is called equidistribution, that I'm going to define in the next slide. So if we have a sequence of closed curves, in this case, for this problem, in a manifold, we will say that they are equidistributed if they obey that asymptotics there. So we can understand this as if we consider the portion of the length of the first k curves, which is contained in U, right? That converges when k goes to infinity to the portion of the volume of the manifold that is contained in U. So an observation is that if we have an equidistributed sequence of curves, then the union of those curves will be dense, because if an open set doesn't intersect any of them, then on the left-hand side of this, we will get 0, right? But on the right-hand side, you always have something positive, so it will not obey the limit that defines the equidistribution. And, well, an alternative formulation for the equidistribution is using integrals of functions. So like somehow average integral of any function f over the first k closed curves converges when k goes to infinity to the average integral over the manifold. And to go from one to the other, one can use like characteristic functions of sets, Borel sets, for example. Okay, so the first result that I want to present is the following. Suppose that we have a closed two manifold, so a surface. Then for a generic metric on it, so generic in the bare sense, there exists an equidistributed sequence of closed geodesics in the manifold, in the sense that it was defined before. So I have to remark that the analog result here, but replacing two-dimensional manifolds by manifolds with dimensions between 3 and 7, and instead of geodesics smoothly embedded compact minimal hypersurfaces, was proved by Marquez, Neves, and Song. And so this is inspired on that result. So this would be a two-dimensional version of that theorem. And something that I didn't mention before is that here we cannot expect to have embedded closed geodesics, because there are certain metrics which only admit, like certain ellipsoids that only admit 3 different embedded closed geodesics, but we can get immersed. Okay, but then we also ask the question of whether we can find a higher dimensional version of this. So if we replace a 2-manifold by an n-dimensional manifold, what can we say about this question? Like, is there still an equidistributed sequence of closed geodesics or a dense sequence or something? So for that, I need to introduce the following object. So instead of geodesics, we will need to work with stationary geodesic nets. So what is a stationary geodesic net? It's a map whose domain is a certain graph. In fact, it's a weighted multigraph, so you have a graph and you can put multiplicities on the edges, which is, okay, so topologically it's an embedding. And, well, along the edges, we ask for some regularity, for example, C2, so that we can differentiate. And it has to be stationary for the length functional. So if we take any one-parameter family of such embeddings from the graph, then well, the derivative of the length will be equal to 0. So it's the same notion as closed geodesic, but replacing a circle by a graph. So the first example is just if we put a circle, we recover an embedded closed geodesic. Then, so here, like if we put the graph gamma to be a figure 8 graph, right? Then we get like this immersed closed geodesic, for example. So we can see the immersed as an embedded stationary geodesic net. And if we put like a domain gamma, this complete graph with 4 vertices, then we get like a tetrahedra, like the one skeleton of an embedded equilateral tetrahedra in the sphere. So in general, like the condition to be a stationary geodesic net, well, there are two conditions. One is that the edges of the graph are mapped to geodesic segments. And the other is that at the vertices, we have like a balancing condition. So for example, in the tetrahedra, like we need the three geodesic segments to meet at 120-degree angles. So in general, the condition is that if we consider the sum of the unit vectors at the vertex B, let's say, with the multiplicity corresponding to the multiplicity of the edges, then that has to sum 0, the sum of the, so that it is balanced. And it verifies the first variation formula. Okay. So with Yevgeny Lyokumovich, we could show the following result about geodesic networks on manifolds. If you take any manifold of dimension greater or equal than 2, and you put a Riemannian metric on it, a generic Riemannian metric, then the union of all the images of the embedded stationary geodesic nets in the manifold forms a dense subset of the manifold. So also there was a version of this for minimal hypersurfaces in ambient dimensions between 3 and 7 by Iri, Marquez, and Neves. And, well, that was previous to the equidistribution. And so we have, well, really a similar story here. So later, we could upgrade this density to equidistribution in collaboration with Jinse Lee for dimension 3, and then I could extend it to n greater or equal than 4 also. So the result is that you take an n-dimensional manifold for any n, which is closed, and for a generic metric on it, you can find an equidistributed sequence of stationary geodesic nets in the manifold. So for dimension 2, you get immersed closed geodesics, but 3 and higher, you get these geodesic nets which have some singularities, or could have some singularities. In fact, we don't know whether they are singular, each of them is singular or not, but it could be. Okay. So, okay, I will talk about, so what's the technique that we use to prove this kind of results, and something that appeared previously on the talks, which is the Almgren-Pitts min-max theory. Mostly in the previous talks, it appeared for codimension 1 cycle, so for k equals n minus 1, but it can be formulated in general. So suppose that we want to construct k-dimensional minimal submanifolds of Riemannian manifold of dimension n, right? A closed Riemannian manifold, for example. Then one can consider the space of Lipschitz k cycles in the manifold with C2 coefficients for the sake of this talk, but the definition makes sense for other coefficient groups, which are like Lipschitz generalizations of closed embedded submanifolds. Okay, we can think of it like that, because if you have a submanifold, you pick a triangulation, and you can view it as a Lipschitz cycle. And then Almgren and Pitts developed Morse's theory for the so-called mass functional. So this mass functional generalizes the k-dimensional volume for smooth submanifolds to this space of mod 2 cycles. And the idea is that the critical points of this functional will correspond to what I call stationary integral k variables. So essentially, this is Lipschitz version of a minimal submanifold of dimension k, like a closed minimal submanifold of dimension k. And so in certain conditions, so for example, when, as discussed in the previous talks, for k equals n minus 1 and n between 3 and 7, these stationary integral variables are in fact realized by minimal hypersurfaces which are smooth, embedded, and closed. So we will study what happens when we take k equals 1, mostly in this talk, and which kind of objects we get. That will be the stationary geodesic networks. I can tell you in advance. Okay, So we have the definition of the volume spectrum. So here, in comparison with other talks, we add like this parameter k that indicates the dimension of the cycles for which we consider the sweep outs. So for us, like the sweep outs are these multi-parameter families f from x to the space of k cycles. So x is some simplicial complex or some cubical complex. And there is a way to define, that I don't have, of course, time to explain it in detail, but in analogy to the talks that we have seen before, there exists a certain cohomology class. So there exists some fundamental class lambda k that belongs to the n minus kth cohomology group of the space of k cycles with two coefficients, okay? And the property that characterizes p sweep outs is that the pullback of this fundamental class to the power of p has to be non-zero, which is the same condition that Jean-Jo described for k equals n minus 1 in his talk. So this as an element in the, like in this case, it would be p times n minus k cohomology group of x, of the space that parameterizes the thing. And so, like, yes. The intuitive idea, for example, for p equals 1 is that if you do in a certain way that I'm going to describe, you glue the family of cycles, of k cycles that you have, you obtain a cycle that represents the fundamental homology class of the manifold. That's sort of the heuristic of a sweep out. So that's why it's sweeping out the manifold. Okay, so we can define this quantity in this min-max way. So we want to, okay, sorry. Let me go back. So we want to minimize the overall p sweep outs, the mass. So precisely what we want to minimize is the supremum of the mass over all the cycles in my family of cycles, parameterized by x, right? So this sequence of numbers is the volume spectrum of the manifold. And so Pitts showed that when we take k equals 1, so 1 cycles, then every p width is realized by a stationary geodesic network. So there exists a certain multigraph, gamma p, that will depend on p and that can be disconnected and have singularities, and etc. And a geodesic network with that domain whose length is equal to the p width. And so somehow here is where it comes the relationship between this volume spectrum and the type of results that we want to prove, like density and equidistribution. Because one can see here that for each p, we have a certain stationary geodesic net. So we would like to have that these gamma p's, for example, is the equidistributed sequence. That is not exactly the result that is proved, but somehow it's inspired by that idea. But the issue is the following. So because we are considering multigraphs, right, it could happen that these omega p's are realized by like the same multigraph with different multiplicities. Yeah, so these gamma p's are like multiples of the same object or of a finite number of objects. We don't know. So in order to understand or to prove the result of equidistribution, we need to understand better the asymptotic behavior of this volume spectrum. But also maybe at this point I want to mention that, so this is true for every n, right? But there is this remarkable result by Chodos Mantoulidis that when you take n equals 2, you can obtain that like the every p width of a surface is realized by a sum with certain multiplicities of like lengths of gamma I, but this gamma I is immersed geodesic. So this is the very big result that we used to prove equidistribution of closed geodesics in dimension 2. But in higher dimension, we only have this result by bits. And so we can only get geodesic networks. OK. So regarding the asymptotic behavior of the p-widths, so the first result that I want to mention is this result proved by Gromov and Guth, where they show that for any manifold, possibly with boundary, compact manifold, possibly with boundary, the p-dimensional widths are bounded by constant that depends on the manifold times this, like p to the power of n minus k over n. Due to an argument of Antoine Song, this estimate is enough to prove the density results for minimal hypersurfaces or for geodesic nets. But if you want to obtain equidistribution, you need a finer estimate. And that, well, was conjectured by Gromov, who proposed this analogy between the volume spectrum of Riemann manifold and the eigenvalues of the Laplacian. So he conjectured that this volume spectrum should obey Weyl law of this type. So there should exist some universal constant that depends only on the dimension of the manifold and the dimension of the cycles that we choose. So that, well, when we take this normalized limit of the p-widths, that because of Gromov-Guth theorem, we conjecture that asymptotically they go like p to the n minus k over n, then that converges to this constant times the normalized volume of the manifold, right? So I will mention what is the status of this conjecture for now. So in 2016, Liukumovich, Marquez, and Neves showed this conjecture for domains in Rn, in fact, not only contractible, but also with some topological condition that is more general. But to avoid the technicalities, I'll mention the contractible. And also they showed it for n-1 cycles in n manifolds. So that's what allowed them to prove all of their density and equidistribution results. And also with certain modifications, Antoine Song used it to prove the Yau conjecture, the existence of infinitely many minimal hypersurfaces in any Riemannian manifold of dimension between 3 and 7. Then later, Guth and Liukumovich studied the case of 1 cycles in 3-dimensional manifolds, and they proved that the Weyl law holds in that case. And recently, I could extend the results for 1 cycles by Guth and Liukumovich to n-dimensional manifold. So the Weyl law is true for 1 cycles in n-dimensional manifolds for every n. And this is what we use to prove the equidistribution of stationary geodesic nets, the theorem that I mentioned before. OK, so I will mention a little bit. OK, maybe go back. So what is the strategy to prove the Weyl law? So first, given the fact that by the work of Liukumovich, Marquez, Neves, we know this on domains of Rn, all the proofs for manifolds consist of like taking a manifold and using the result, like triangulating the manifold and trying to construct an optimal p-sweep out of the manifold by an optimal p-sweep out of the different pieces of the triangulation. So the main difficulty to do that is the following. So suppose that we have here like just the manifold consists of a rectangle, okay, that is like 2 cubes, only 2 simplices, to do a very simple example. And so here we have in the square Q1 or the simplex Q1 a certain family F1 of X, and in the other F2 of X, right? That is like an almost optimal p-sweep out in terms of the mass, of maximizing the mass. Like it minimizes the maximum of the mass. Okay, then the problem is that these two families, if I just take the family which is like the sum, so the black and plus the red one cycles, then that is not a family of cycles relative to the rectangle, right? Because it has a lot of boundary points in the common interface between the two cubes, right? And yes, the Weyl Law is about, or the p-widths are defined by min-max on space of cycles. So we need to work with continuous families of cycles. So the something that we can do in the case that is depicted here, so dimension 2 and one-dimensional cycles, is to add a family F3 that is supported in the common interface between Q1 and Q2, right? A collection of segments whose boundary is equal to like the boundary of F1 minus the boundary of F2. So now if we consider the family which is F1 plus F2 plus F3, assuming that we can construct F3 in a continuous way, then we get a family of cycles, right? Because we build F3 on purpose so that it cancels that boundary. And the good thing of this is that, so we're doing this for each P, so this F1, F2, F3 depend on P. The total amount of mass that we're adding, or length, like the length of F3, right? So the length of F3 of X, because this is parametric, is less or equal than just the length of the intersection of the two simplices, right? No matter how many points I have from F2 and F1, I can find a collection of segments whose boundary is boundary F2 minus boundary F1, and the total length is at most this, which is constant because the triangulation that I'm picking is fixed. So then when I multiply by the corresponding power, so then I need to multiply by P to the power of minus 1/2 in this case, like by the Weyl Law, the amount of mass that I am adding. So this is a constant, right? So when I multiply by P to the minus 1/2, it goes to 0 as P goes to infinity. So asymptotically, the amount of mass that I am adding is 0. So roughly speaking, this is the type of construction that one does to prove it. In this case, k equals 1, n equals 2. And in fact, in the codimension 1 case, one can argue in a similar way. OK. But what happens when the codimension is higher? So in the picture will be 3-dimensional manifold. So I have, again, like on the left, I have F1, that is a p sweep out of this square. Then I have F2, a p sweep out of the square. Again, the boundaries do not match. But now the problem is that, so here I only put like 5 points. But you can imagine, later I will do pictures, that you can have a lot of points here in this intersection. Like it's possible to have an arbitrary number of points. The same was possible in the previous situation. But what is the difference? That, like in this case, right, when I start adding segments to compensate for those points, as I did in the other case, the total mass of this F3 is unbounded. Like if I have an extremely large number of points that are distributed in certain ways, I am forced to add one chain F3, which is extremely long. OK. But Guth and Jakubowicz proposed the following solution for this problem. Sorry. So first of all, the problem of the number of points, they say, OK, we can change these two families, F1 and F2, by two families which are nearby and which have controlled boundary. So the mass of the boundary of F1 prime and F2 prime, we want it to be controlled by a certain quantity so that then we can prove the Weyl Law, essentially. And once you have this F1 prime, F2 prime with controlled boundary, then what you get is like some family of points, right, in the square in the interface. And you want to add one family of one chains, F3, whose boundary is your family of points. So that is to prove a parametric version of the isoperimetric inequality, because we want this F3 to have controlled mass. So it is exactly like I have a certain cycle. I want to find k plus 1, in this case 1 cycles, whose boundary is my family of cycles, but has a controlled mass. So this is the strategy that they proposed, and they could prove it for k equals 1, n equals 3. And then, well, I could extend this to k equals 1 and n higher. So I will try to briefly explain like what do I mean by these two things, parametric coherent inequality and isoperimetric. And like with that I will conclude the talk. So what do we mean by coherent inequality? So before I was saying that we had certain like F1, for example, and it may happen that the intersection with the boundary consists of a very large number of points. So here there is an example of one chain that has a finite mass, and you can even make it as small as you want by rescaling. Right? So it's a tree that ramifies into 3 parts at each point. But if you do this like countably many times, then the intersection with the boundary consists of infinitely many points. Right? So the mass of the boundary, with the mass here I mean the number of points, or when I talk about the mass of a zero cycle, yeah, that is infinite. And this phenomenon can happen with in any dimension. I'm just putting a dimension 1, but it can happen in any dimension. Okay, but maybe what we can do is, instead of considering tau, we can restrict tau to a smaller domain, slightly smaller, of this form like ms that I put here. So it's the set of points at distance at least s from the boundary. And so now when I restrict tau to this smaller domain, then the mass of the boundary decreased significantly, right? So more precisely, what we can prove is this lemma, this is the coherent inequality, or one form to state it, that if you give me any number epsilon greater than 0, then there will exist some number s between 0 and epsilon, so that if I restrict my cycle to the square ms, like s distance away from the boundary, then the boundary of that restriction has mass at most the mass of the original tau over epsilon. So essentially what we would like to do with this parametric coherent inequality I mentioned before is to have something like this, but for a parametric family. So this result is for only one chain tau. Then imagine that you have a family of chains like tau of x, continuous, and you want to prove something like that. So you want to decide an s of x for each x, so that the mass of the boundary of tau restricted to m s of x is less or equal than the mass of tau of x over epsilon. Okay, so for each x I want to choose such s, but I would like to do it continuously because we want to have continuous families. But sadly that's not possible. Guth and Jokumovich showed a counterexample where you cannot choose this s continuously. So the actual formulation of the parametric coherent inequality is that if you give me a family of 1 cycles whose boundary is very large, then I want to perturb it a little bit to produce a new f prime, so that the new f prime doesn't have much more mass than the original family somehow, because we are interested in constructing these optimal p-sweepouts. And the mass of the boundary is also bounded. So that's what we will mean by parametric coherent inequality. And so here's the precise statement. So we consider, as I said above, like n-dimensional manifold and families of continuous families. So here there is, well, this parameter that is not very important, but can be any number between 0 and 1 that is auxiliary in the construction that we do. And then we can produce a family F prime, which is very close to F in flat topology, as close as we want. And it verifies that, so this is the second item above, like the mass of F prime is not much bigger. So this epsilon p is a parameter that goes to 0 as p goes to infinity. So somehow have an increase, but not that much. And then like this term is small enough to prove the Weyl law, because for the Weyl law, we need to multiply by p to the minus n minus 1 over n. So if you choose alpha very small, still after you multiply by that factor, this goes to 0, essentially. And the mass of the boundary is essentially bounded by constant times p, but with a slightly worse power, 1 plus alpha, p to the 1 plus alpha. Okay, and finally, so the other result that I said that one has to prove is parametric, isoperimetric inequality. So we have like this family of points in the common intersection between like two cubes, for example, right? And we assume that this family is contractible. Then we can construct a family of one chains so that, yeah, the boundary is equal to F. So actually, if we only want this, it is a consequence of being contractible. Any contractible family of zero cycles like admits some continuous filling. But the complicated thing is to get a filling whose mass is bounded, or bounded by a number or by a quantity that is good enough to prove the Weyl law. So we obtain this type of bound. So we get a bound by the constant that depends on the manifold times, so the original family, the mass of the original family, multiplied by this, p to the minus 1 over n, and then plus this other power, p to the n minus 1 over n. Yeah, and the same result holds for families of relative cycles, also with C2 coefficient. And essentially, if we combine those two, we can perform the argument that I sketched before to prove the Weyl law by gluing like almost optimal sweep outs on simplices of the triangulation of a manifold that we pick. And I think that's all. Thank you very much for listening.